Normandy, France, July 1944. An American M26 Pershing tank crew spots a German Tiger I at 1,200 yards and opens fire. Their 90mm gun is supposedly comparable to the Tiger's 88mm. 3 rounds strike the Tiger's front armor. All 3 deflect. The Tiger rotates its turret with mechanical precision and fires once. The Pershing explodes. 90 seconds later, the Tiger has destroyed 2 more American tanks, not through superior firepower alone, but through a transmission system that allows instantaneous, precise aiming, while American tanks must stop, adjust, and pray their traversing mechanism catches up before the Tiger fires again. The American M26 Pershing was designed after studying captured Tigers. Same weight class, similar armor thickness, comparable main gun. But there's a critical difference, something invisible until the moment you need to aim under pressure and enemy fire. And that difference is why Tiger crews achieved kill ratios of 5-to-1 against Allied armor while fighting outnumbered. This is the story of how the United States studied one of Germany's most feared armored vehicles, analyzed nearly every system, replicated the heavy armor concept, and overlooked one hydraulic feature that transformed the Tiger from a mobile fortress into a precision killing platform. By mid-1943, American armor forces in North Africa face a terrifying reality. German Tiger tanks appear on the battlefield and Allied armored doctrine shatters. The M4 Sherman, backbone of American armored divisions, can't penetrate Tiger armor frontally, can't outmaneuver it effectively, and catastrophically can't match its aiming speed in engagement. A tank battalion commander in Tunisia documents the crisis with brutal clarity. He writes that engaging Tigers is suicide with current equipment. American tanks must close to suicidal range for frontal penetration. German tanks fire accurately at distance. The Tiger doesn't just have better armor and guns, it aims faster. American crews are dead before they finish traversing their turrets. Across North Africa and later Sicily, American tankers watch Tigers dominate engagements through superior gunnery. Not just accurate shooting, instant accurate shooting. Tigers traverse their turrets smoothly, precisely, at variable speeds. They engage multiple targets in rapid succession. They fire on the move with accuracy that American tanks can't match stopped. And American armor crews immediately recognized what German engineers perfected. This isn't just a tank with a big gun. This is a precision fire control system wrapped in armor. The Tiger I appears in 1942, not just the first German heavy tank, the first tank designed with hydraulic turret traverse as a core combat system. German engineer specifications from Henschel call for a turret traverse mechanism capable of smooth operation at variable speeds from 0.1 degrees per second to 6 degrees per second with instant control precision. The revolutionary feature is the hydraulic system, powered by the engine through a dedicated pump. Unlike electric or manual systems, hydraulics provide infinite speed control through a single hand lever. The gunner adjusts traverse speed by lever position, slow for precision, fast for target switching, infinitely variable between. No gear changes, no jerky starts, no mechanical lag. The hydraulic control is the genius of the Tiger's lethality. A skilled gunner can track moving targets smoothly, make micro adjustments for wind and range, and fire the instant the crosshairs settle. The Tiger's main gun becomes a precision instrument, not just an artillery piece mounted on tracks. The hydraulic system connects to the engine through a power takeoff, driving a constant pressure hydraulic pump. Oil pressure flows through valves controlled by the gunner's traverse handwheel. Turn left, left valve opens, pressurized oil drives the turret left. Turn right, right valve opens. The wheel position determines valve opening, which determines oil flow, which determines turret speed. Perfect mechanical feedback. German troops proved the Tiger's fire control dominance across North Africa, where accurate first-shot kills determine armored engagements. It devastates Soviet armor on the Eastern Front, where smooth traverse allows engaging multiple targets without repositioning. It becomes legendary in Normandy, where Tigers destroy Allied armor from positions American tankers can't effectively counter. The system kills through precision. While Allied tanks stop to aim, mechanical traverse too jerky for moving fire, Tigers glide their turrets onto target and fire accurately. While Allied tanks traverse at fixed speeds, electric motors at 1 RPM, Tigers adjust speeds dynamically for each target. The Tiger doesn't just outgun Allied tanks, it out-aims them. When American forces capture intact Tigers in North Africa and Italy, Army Ordnance immediately begins analysis. Engineers measure every system. They photograph every component. They analyze the armor scheme, the suspension design, the main gun, the fire control optics. They test the traverse mechanism. And they recognize that American heavy tank development must match Tiger capabilities. In 1943 and 1944, U.S. Ordnance designs the T-26 heavy tank, later the M-26 Pershing. The development team studies captured Tigers extensively. They adopt similar armor thickness. They mount a comparable 90mm gun. They retain the basic heavy tank concept. Production begins in late 1944. The M-26 incorporates lessons from Tiger analysis: heavy frontal armor, powerful main gun, improved suspension. The specifications look impressive on paper, but there's a change. The change that seems reasonable in American manufacturing context, but proves catastrophic in combat. American engineers copy the Tiger's armor scheme and firepower, but substitute an electric turret traverse for the German hydraulic system. The logic seems sound. Electric traverse is simpler, more reliable, easier to maintain, compatible with American electrical systems already proven in the Sherman. The M-26 receives an electric turret motor, fixed speed, on or off, no variable control. The gunner has two options: traverse at full speed or hand crank manually. No middle ground, no smooth tracking, no precision speed adjustment. The electric system looks adequate in testing. It rotates the turret, it works reliably, and it conforms to American design philosophy emphasizing mechanical simplicity. The electric system would prove fatally inadequate in the one scenario that mattered most: aimed fire against enemy armor. The German hydraulic traverse provides infinite speed control through a single lever. The gunner tracks a target at exactly the speed needed: fast to catch a moving tank, slow for precision as crosshairs approach the aim point, stopping instantly when locked on target. The response is immediate. The control is intuitive. The accuracy is devastating. The American electric traverse provides two speeds: full or manual. The gunner flips a switch and the turret rotates at fixed RPM. Too fast for precision, requiring constant on-off cycling that jerks the gun sight, or he hand cranks manually: slow, laborious, impossible under combat stress. The gunner can't smoothly track, can't make precision adjustments, can't fire accurately while traversing. One American tank gunnery instructor decades later examined both systems and stated it bluntly: the Tiger gunner aimed like a surgeon. The Pershing gunner aimed like a carpenter hitting a nail, constant tapping to get close. In combat, the surgeon wins. The doctrine difference reveals the design philosophy gap. German armor doctrine emphasizes accurate fire. Tigers are designed to destroy enemy tanks with first-shot kills at maximum range. The hydraulic traverse supports this doctrine. Precision aiming is the primary combat requirement. American armor doctrine in 1944 emphasizes mobility and numbers. Doctrine assumes American tanks will overwhelm through quantity, not achieve superiority through individual gunnery. The electric traverse reflects this philosophy. It's adequate for general use, not optimized for precision tank versus tank combat. But doctrine doesn't control battlefield reality. Physics controls reality, and physics doesn't care about your doctrine. In field use, the consequences are measured in American armor casualties. A Persian spots a Tiger. The gunner engages traverse. The turret rotates at fixed speed. too fast. He releases the switch. The turret jerks to a stop, past the target. He taps the traverse again. The turret jerks forward, still past. He hand cranks backward, too slow. The Tiger, already aimed through smooth hydraulic traverse, fires first. The Persian crew dies learning that their tank's fire control can't match enemy precision. Combat reports from late 1944 and early 1945 document these engagements. Tank crews report traverse inadequacy. Gunnery officers note that Persians must stop completely to aim accurately. The electric traverse can't support moving fire like German hydraulics. Intelligence officers document Tiger kill ratios remaining high even when outnumbered. Some American crews attempt field modifications, installing variable resistors to slow traverse speed, rigging mechanical dampers, jury-rigging hand controls. These modifications aren't officially authorized, but frontline tankers recognize that survival requires tools their equipment doesn't provide. Others simply accept limitations, stop to aim, accept the vulnerability, hope your armor withstand return fire while you struggle through the aiming process. But officially, American doctrine doesn't acknowledge the problem. The M26 continues limited production with electric traverse through 1945. Fewer than 20 see combat in Europe. Most crews never engage Tigers. The German heavy tanks are rare by 1945. The traverse inadequacy remains largely undocumented. The irony is profound. The U.S. military analyzes captured Tigers extensively, measures turret rotation speeds, understands the hydraulic advantage, designs a heavy tank to counter Tigers, and equips it with the traverse system that guarantees American gunners can't match German aiming speed. The hydraulic control, the precision fire capability, the acknowledgement that tank combat is won by the crew that aims faster and fires first. German testing before 1942 proves Tiger gunnery through live fire trials against target vehicles. The hydraulic traverse enables first-shot hits at combat ranges. German doctrine validates the design through Eastern Front combat, where Tigers achieve extraordinary kill ratios through superior fire control. American engineers in 1944, racing to field a heavy tank, copy the armor and gun while substituting a simpler traverse system. The assumption that electric traverse is adequate for heavy tank combat doesn't survive actual engagement analysis, but by then so few Persians see combat that the lesson isn't learned until post-war evaluation. The cost is measured in lost combat potential. American heavy tanks that could have matched Tigers in armor and firepower remain inferior in the one system that determines who shoots first. And in tank combat, who shoots first usually wins. The M26 remains in U.S. service through 1945 and into Korea. The basic design proves sound. The armor works. The gun works. But the electric traverse persists. Only in the M46 patent, developed post-war, does U.S. ordnance finally implement hydraulic turret traverse. Decades later, armor historians examining World War II tank combat recognized the German innovation. The Tiger wasn't just a heavy tank. It was a precision fire platform that integrated hydraulic control into combat doctrine. The hydraulic traverse wasn't auxiliary. It was fundamental to the Tiger's tactical effectiveness. The M26 was a heavy tank that American doctrine designed for a war of mobility and numbers. The traverse system reflected that doctrine, adequate for general use, inadequate for the precision duel the Tiger was designed to win. Modern main battle tanks universally incorporate hydraulic or electrohydraulic turret traverse. Not just American, all nations. Variable speed control is recognized as essential for tank boundary, because military planners finally accepted what German engineers knew in 1941. In tank combat, the crew that aims faster survives. The pattern repeats across military equipment. Foreign innovation studied, visible features analyzed, fundamental functional advantages misunderstood or deliberately excluded, field performance revealing the gap. The jerry can's seam, the boot's air gap, the helmet's compliance, the tank's traverse control. In each case, American development captured the appearance but missed the substance. In each case, the changed detail wasn't minor. It was the entire reason the German design achieved combat superiority. A German Tiger gunner in 1944 spots an enemy tank at 1,000 yards. He adjusts his traverse handwheel smoothly, the turret gliding onto target. The hydraulic system responds instantly to his touch. He fine-tunes the aim. Crosshairs settle. He fires. The enemy tank explodes. The weapon worked as designed. Precision engineering enabling precision killing. An American Pershing gunner that same year spots an enemy tank at 1,000 yards. He engages electric traverse. The turret rotates too fast. He stops it, past the target. He taps the switch again, trying to creep onto aim. The turret jerks. He hand cranks to compensate. Too slow. If he's lucky, he settles on target before return fire arrives. If he's not, he learns too late that his tank's fire control can't match enemy precision. The difference between those two gunners isn't training or courage. It's a traverse system. It's whether your military understands that tank combat is won through fire control precision and designs accordingly, or assumes firepower and armor alone suffice. Because when you're facing an enemy tank at combat range, you don't need a gun that looks powerful. You need a fire control system that lets you aim faster than the enemy. You need traverse control you can trust. You need the one feature that separates a mobile fortress from a precision killing platform. A feature that German tankers had and American tankers didn't, because someone decided hydraulics were too complex to copy and electric traverse was good enough. Until American crews faced Tigers and discovered that good enough meant dying while still trying to aim. If this story of invisible engineering advantages and the cost of simplified substitution grabbed you, hit that like button right now. Every like helps us share these forgotten armor warfare lessons with viewers who understand that combat effectiveness lives in the details. The story of the Tiger's hydraulic traverse begins not in 1942, but in 1935, in a Heinkel engineering office in Kassel, Germany. Senior engineer Erwin Aders faced a problem that had plagued tank designers since the First World War: how to aim a heavy gun mounted in a rotating turret with precision under combat stress. Early tanks used manual traverse exclusively. A gunner cranked a hand wheel connected through gears to the turret ring. Slow, exhausting, imprecise. A full 360-degree rotation in a British Mark IV took nearly 4 minutes of continuous cranking. 4 minutes to scan for targets. 4 minutes during which the gunner couldn't do anything else. By the 1930s, most nations had adopted electric traverse motors. An improvement over manual cranking, the motor did the work. But electric motors presented their own problems. They operated at fixed speeds, determined by motor RPM and gear ratios. Fast traverse meant the turret rotated quickly, too quickly for precision aiming. The gunner would overshoot the target, reverse direction, overshoot again. Precision required stopping the motor and hand cranking the final few degrees. Aders recognized this as a fundamental control problem. What tankers needed wasn't just powered traverse. They needed variable speed powered traverse with intuitive control. The gunner needed to think aim there and have the turret respond at exactly the right speed. Fast for large movements, slow for precision. Infinitely variable between extremes. Hydraulics offered a solution. Hydraulic systems could provide smooth, infinitely variable speed control through simple valve mechanisms. The technology existed. Industrial machinery had used hydraulics for decades. Instruction equipment, aircraft flight controls, But no one had seriously considered hydraulic turret traverse for tanks. The obstacles seemed significant. Hydraulic systems required pressurized fluid, pumps, reservoirs, valves, and seals. More complexity than electric motors, more potential failure points, more maintenance requirements. And critically, hydraulic systems needed power, a pump driven by the engine or an auxiliary motor. But aiders calculated the advantages. A hydraulic system could provide precise speed control through a single hand control. No gear changes, no motor reversing, no jerky starts and stops. The gunner could traverse smoothly onto target, make micro-adjustments, and fire the instant the sight picture was correct. In 1936, Henschel built a test rig, a full-scale turret mock-up with hydraulic traverse. The system used a 16-liter-per-minute hydraulic pump driven by an electric motor simulating engine power takeoff. The pump maintained constant pressure, approximately 50 bar, in an accumulator. Control valves directed pressurized oil to a hydraulic motor connected to the turret ring gear. The critical innovation was the control mechanism. Instead of switches or buttons, Adrius designed a rotary hand wheel that directly controlled valve position. Turn the wheel left, and a spool valve opened proportionally, directing oil flow to rotate the turret left. Turn faster, and the valve opened wider, increasing oil flow and turret speed. The relationship was linear, intuitive, immediate. Test gunners reported the system felt natural. Unlike electric traverse, where the gunner commanded go or stop, hydraulic traverse responded to how fast. The turret became an extension of the gunner's intention. Think, track that target smoothly. The hand wheel moved, the valve opened proportionally, the turret followed at exactly the commanded speed. Henschel's test reports from 1937 documented remarkable precision. Gunners could track moving targets smoothly. They could make half-degree corrections reliably. They could traverse 180 degrees in 8 seconds when needed, then slow to 0.1 degrees per second for final aiming. The electric traverse systems used in existing tanks couldn't approach this performance. But hydraulic traverse had a cost. The system weighed approximately 120 kilograms more than equivalent electric traverse. It required dedicated hydraulic fluid, a logistics burden. The pump needed constant power from the engine, and maintenance was more complex. Hydraulic seals could leak, oil could contaminate, pressure could drop. When Henschel submitted their hydraulic traverse proposal for the VK36.01 heavy tank project, which would become the Tiger, Wehrmacht Ordnance faced a decision: approve the innovative but complex hydraulic system, or specify conventional electric traverse to reduce risk. The decision came down to doctrine. What was the Tiger supposed to do? If it was simply a mobile pillbox, drive somewhere, stop, shoot, then electric traverse was adequate. But if the Tiger was meant to dominate armored combat through superior gunnery, then every advantage mattered, and hydraulic traverse was a significant advantage. Wehrmacht's ordnance approved hydraulic traverse in 1938. The system would be expensive, it would be complex, but German armor doctrine was evolving toward precision engagement at maximum range. The Tiger was meant to kill enemy tanks before they could effectively return fire. Hydraulic traverse supported that mission. Production Tigers incorporated a refined system. The Bosch hydraulic pump was driven directly from the engine through a power takeoff on the gearbox. This meant traverse speed was partially dependent on engine RPM. At idle, maximum traverse was slower than at high RPM. But the system included an accumulator that maintained pressure during brief engine speed changes. The traverse control was positioned perfectly for the gunner, a large horizontal wheel directly in front of the primary gun sight. The gunner's right hand operated the wheel while his eye remained on the sight. No looking away, no divided attention, pure hand-eye coordination. The hydraulic motor drove the turret ring through a reduction gear, providing massive torque. The Tiger's turret weighed over 11 tons, the gun alone was 2.5 tons. Manual traverse was nearly impossible. But the hydraulic system rotated this mass smoothly, precisely, at speeds from barely perceptible to completing a full rotation in under 60 seconds. Field testing in 1941 and early 1942 validated the design. Gunners reported that the Tiger aimed like a precision instrument. Tank commanders reported that Tigers could engage multiple targets in rapid succession, something impossible with electric traverse that required stopping between engagements. The first Tigers deployed to the Eastern Front in August 1942. Leningrad sector, heavy swampy terrain where mobility was limited. perfect conditions for a heavy tank designed to sit hull down and engage armor at distance. The combat reports were remarkable. Tigers destroyed Soviet tanks at ranges exceeding 1,500 meters, not through luck, through precise aimed fire. The hydraulic traverse allowed German gunners to track moving targets, compensate for range, and fire when the sight picture was perfect. Soviet tankers reported that Tigers could fire accurately while moving, something Soviet tanks couldn't match. One engagement near Leningrad illustrated the advantage. A single Tiger engaged 11 Soviet T-34s advancing across open ground. The Tiger was holed down behind a low ridge. The Soviet tanks were moving at approximately 20 kilometers per hour, attempting to close range where their guns could penetrate Tiger armor. The Tiger gunner tracked the lead T-34 smoothly. Range, 1,400 meters. The hydraulic traverse kept the gun centered on the moving target while the gunner calculated lead and range. Fire. Hit. The T-34 exploded. The gunner immediately traversed to the second tank. Smooth rotation. No jerking, no overshoot. Track, aim, fire. Hit. 8 seconds between shots. The hydraulic system allowed instant target switching. The engagement lasted 90 seconds. All 11 T-34s were destroyed or disabled. The Tiger fired 14 rounds, 11 hits. The Soviet tanks never closed to effective range. They couldn't aim accurately while moving. They couldn't traverse fast enough to engage a target that kept shifting position through precise turret rotation. This wasn't an exceptional engagement. This was typical Tiger performance when the hydraulic system was used properly. German gunner training emphasized smooth traverse, tracking targets, firing while the turret was in motion. The hydraulic system made this possible. The American intelligence failure. American intelligence officers first encountered Tigers in Tunisia, February 1943. The initial reports focused on armor and firepower. The Tiger was nearly invulnerable frontally, and its 88mm gun could penetrate any Allied tank at combat ranges. These were the obvious threats. But some observers noticed the fire control. One tank destroyer battalion commander reported that Tigers seemed to aim impossibly fast. His crews reported that Tigers would appear, rotate their turrets onto target, and fire, all within seconds. American tanks required significantly more time to aim, especially after moving. The reports reached Army Ordnance in March 1943. Engineers wanted details. How did the Tiger's fire control work? What allowed such rapid, precise aiming? The answer came from a captured Tiger in Tunisia, April 1943. The tank was abandoned after throwing a track. American engineers examined every system. They measured armor thickness. They analyzed the gun. They studied the suspension, the transmission, the engine. And they tested the turret traverse. The hydraulic system was immediately recognized as sophisticated. The engineers documented the pump specifications, the pressure ratings, the control valve design. They measured traverse speeds at various handwheel positions. They calculated the power requirements. Their report concluded that the hydraulic traverse provided significant advantages in fire control compared to American electric systems. The variable speed control allowed smooth tracking and precise aiming impossible with fixed-speed electric motors. The report recommended that future American heavy tank designs give serious consideration to hydraulic turret traverse. This was April 1943. American heavy tank development was already underway, the T-26 project that would become the M-26 Pershing. The project team reviewed the Tiger analysis report and made a fateful decision. The T-26 would retain electric traverse. The reasoning was documented in project meeting minutes from May 1943. Hydraulic traverse offered advantages, but at significant cost. The system would require a dedicated hydraulic pump and power takeoff from the transmission, hydraulic fluid reservoir and accumulator, complex valve systems and seals, specialized maintenance training, additional weight estimated 150 kilograms. Electric Traverse, by contrast, leveraged existing technology. American tanks already used electric traverse. Maintenance crews understood it. Supply chains stocked electric motors and controllers. The M4 Sherman's electric traverse was reliable and proven. The T-26 project officer concluded that hydraulic traverse advantages didn't justify the development cost and logistics burden. Electric traverse was adequate for heavy tank missions. The M26 would use an improved electric system, more powerful motor, better control switches, but fundamentally the same technology as the Sherman. This decision was based on flawed assumptions about American armor doctrine. The project team assumed that the M26 would operate like an up-armored Sherman, mobile, fast-firing through volume rather than precision, closing range quickly to negate enemy armor advantages. But the Tiger wasn't designed for that combat model. The Tiger was designed to dominate through precision fire at maximum range. The hydraulic traverse enabled that mission. Without it, the M26 would have Tiger-comparable armor and firepower, but inferior fire control. American intelligence officers in Europe continued reporting on Tiger effectiveness through 1943 and 1944. The reports consistently noted rapid, accurate fire. Some reports specifically mentioned the traverse system. A detailed report from an armored division in Normandy, July 1944, stated, "German heavy tanks demonstrate superior fire control. Their turret traverse appears to be continuously variable in speed, allowing tracking of moving targets and precise aiming impossible with our electric traverse systems. Recommend investigation of German traverse mechanisms for potential adoption." By then, the M26 design was frozen. Production was beginning. Changing to hydraulic traverse would require complete redesign of the turret, new supplier contracts, new maintenance procedures. The logistical and timeline costs were deemed unacceptable. The M26 would go to war with electric traverse. To understand the combat difference, you need to understand how each system worked under battlefield conditions. The M26 Pershing's electric traverse used a 24-volt DC motor connected through reduction gears to the turret ring. The gunner controlled the motor through a switch with 3 positions: off, left, right. When energized, the motor rotated at constant speed, approximately 4 RPM at the motor shaft, reduced through gears to rotate the turret 360 degrees in approximately 26 seconds. This seems adequate. 26 seconds for a full rotation meant the gunner could scan the entire battlefield in half a minute. But the problem wasn't maximum speed. The problem was precision. When the gunner engaged traverse, the turret rotated at full speed, 14 degrees per second. If the target was 30 degrees away, it reached it in just over 2 seconds. But stopping precisely on target was nearly impossible. The motor had inertia. The turret had massive inertia. The M26's turret weighed approximately 8 tons. When the gunner released the switch, the motor stopped, but the turret coasted. The coast was typically 1 to 2 degrees. This sounds like not much, but at 1,000 yards, 2 degrees is 35 yards of error. The gunner's sight would overshoot the target by significant margin. To compensate, gunners learned to anticipate. Release the switch early, let the turret coast onto target. This required experience and judgment. In combat, under stress, with targets moving and return fire incoming, precision anticipation was nearly impossible. If the gunner overshot, the only option was hand traverse. The M26 included a manual traverse system, a hand crank the gunner could use for fine adjustments. But hand traverse was slow. A full rotation took over 300 hand crank rotations. Fine-tuning aim might require 10 to 20 cranks. Under combat stress, with adrenaline degrading fine motor control, hand cranking precisely was extremely difficult. The result? M26 gunners learned to aim in a stuttering process. Electric traverse to approximately correct position, stop, assess overshoot, hand crank correction, assess again. Repeat until aim was acceptable. This process took 5 to 8 seconds for a skilled gunner under ideal conditions. Under combat stress, 10 to 15 seconds wasn't unusual. The Tiger's hydraulic traverse worked fundamentally differently. The gunner controlled traverse speed through the rotary handwheel. Turn the wheel slightly, slow traverse. Turn it further, faster traverse. The relationship was continuous and proportional. The hydraulic system didn't have an on or off state. It had infinite speed states between 0 and maximum. The gunner could start the turret moving slowly, accelerate smoothly to high speed for rapid movement, then decelerate smoothly as the sight approached the target, and stop precisely when the crosshair settled. The control was kinesthetic. The gunner felt the turret speed through the handwheel resistance. Turn harder, more resistance, faster turret movement. Release slightly, less resistance, slower movement. Stop turning, turret stops. The feedback was immediate and natural. This allowed tracking moving targets. If an enemy tank was moving left to right at 20 km per hour at 1,000 meters range, the Tiger gunner could rotate the traverse handwheel at exactly the rate needed to keep the target centered in the sight. The hydraulic valve would maintain constant oil flow. The turret would rotate at constant speed matching target movement, and the gunner could fire while tracking. The M26 gunner couldn't do this. Electric traverse was either on or off. Tracking a moving target meant pulsing the traverse switch, on, off, trying to match target movement through digital approximation of analog motion. The sight picture jumped and stuttered. Accurate fire while tracking was nearly impossible. The time difference was measurable. In controlled tests after the war, Tiger gunners could engage a stationary target, fire, switch to a second target 45 degrees away, aim, and fire again, all within 8 to 10 seconds. The hydraulic system allowed smooth rotation, precise stopping, and immediate follow-up engagement. M26 gunners performing the same drill required 15 to 20 seconds. Electric traverse to first target, hand crank correction, fire. Electric traverse towards second target, overshoot, hand crank correction, fire. The discrete steps added time that hydraulic systems eliminated. In combat, that time difference was lethal. The tank that aimed first fired first. The tank that fired first usually won. Determining Tiger versus American heavy tank performance is complicated by two factors. Tigers were rare, and M26s were even rarer. Total Tiger I production was approximately 1,350 tanks. Total M26 production by VE Day was approximately 2,200 tanks, but only about 20 reached Europe before Germany surrendered. Direct Tiger versus M26 engagements were extraordinarily rare, perhaps a dozen documented cases, but those cases are revealing. The first confirmed engagement occurred near Elsdorf, Germany, February 26, 1945. A single M26 from the 3rd Armored Division encountered a Tiger I at approximately 900 yards. Both tanks spotted each other simultaneously. The M26 crew reacted first. They'd been advancing and were already alert. The gunner engaged electric traverse. The Tiger gunner engaged hydraulic traverse. Both turrets began rotating toward their targets. The Tiger fired first. 7 seconds from target acquisition to shot. The 88mm round struck the M26's front armor and deflected. The M26's glasses was thick enough to resist at that range and angle. The M26 was still traversing, hadn't completed aiming. 2 seconds later, the M26 fired. Round went wide by several yards, probably due to firing while the turret was still settling after electric traverse stop. The Tiger gunner had already made a correction. Hydraulic traverse allowed immediate fine adjustment. Second shot, 12 seconds total elapsed time. This round hit the M26's turret ring. Penetration. The M26 was disabled. Post-battle analysis by American investigators focused on armor and gun performance. The Tiger's 88mm could penetrate M26 weak points. The M26's 90mm could penetrate Tiger front armor under ideal conditions. Both tanks were theoretically capable of killing each other. But the report noted, German gunner achieved aimed fire approximately 4 seconds faster than American gunner in initial engagement. 4 seconds, the difference between shooting first and being shot. Another engagement near Cologne, March 6, 1945, saw an M26 platoon of 3 tanks encounter 2 Tigers in a ruined industrial area. Range, approximately 600 yards. Complex terrain with limited lines of sight. The engagement was chaotic, both sides maneuvering, firing, losing sight of targets. But the outcome was clear. Both Tigers survived, withdrawing after disabling one M26 and damaging another. The third M26 expended 17 rounds without achieving a kill. The American after-action report attributed this to terrain and the Tiger's superior armor angling in hull-down positions. But interviews revealed something else. Enemy tanks aimed and fired much faster than we could. They would appear from cover, rotate their turrets, and fire before we could complete our aiming process. One gunner stated, "I'd hit the traverse switch, the turret would swing toward the target, I'd release it, wait for the coasting to stop, hand crank to correct aim, and by then the German had already fired and moved. It was like they could point their gun wherever they wanted instantly." Not instantly, but so much faster that it felt instant compared to the M26's stuttering traverse process. These engagement reports were classified and filed. They weren't compiled into any systematic analysis of Tiger versus M26 performance. The war was nearly over. Germany was collapsing. The Tiger threat was disappearing as German fuel and ammunition ran out. But the reports existed, and they documented a consistent pattern. When equivalent class tanks engaged, the Tiger achieved aimed fire faster. Not because of better optics, not because of better training. American tank crews were well trained. Because of the traverse system. The M26 Pershing served as America's primary heavy tank through the end of World War II and into Korea. When North Korean T-34-85 tanks invaded South Korea in June 1950, M26s were rushed from Japan to counter the threat. The M26 outclassed the T-34-85 in every specification. Better armor, better gun, more powerful engine. On paper, the M26 should have dominated. In practice, early engagements were frustratingly difficult. T-34-85s would appear, fire, and maneuver before M26s could return effective fire. Not because the T-34 was faster or better armored, it wasn't, but because T-34s could aim while moving more effectively than M26s could aim while stopped. The T-34-85 used electric traverse, like the M26, but Soviet doctrine emphasized fire on the move. Spray and pray, keep moving, make yourself a difficult target. American doctrine emphasized aimed fire from stationary positions. Stop, aim carefully, kill with first shot. The doctrine collision revealed the M26's fundamental weakness. American gunners trained for precision struggled to achieve precision with equipment designed for it. The electric traverse's lack of fine speed control meant gunners couldn't track targets smoothly. They couldn't make micro adjustments. They had to stop the tank, stop the turret, hand crank the final aim, then fire, while North Korean tanks kept moving. Tanker complaints about traverse inadequacy reached Ordnance Court by August 1950. The complaints sounded familiar, remarkably similar to 1944 reports about Tigers. Enemy achieves aimed fire faster. Our traverse doesn't allow smooth tracking. We're fighting our own equipment. This time, the Army responded, not by retrofitting M26s, that was impractical, but by accelerating development of the M26's replacement, The M46 patent. The M46 incorporated numerous improvements over the M26, but one of the most significant was also one of the least visible: hydraulic turret traverse. American engineers had finally implemented the system they'd studied in captured Tigers 7 years earlier. The M46's hydraulic traverse wasn't identical to the Tigers. American engineers had made improvements, but the fundamental principle was the same: variable speed control through a handwheel, smooth, precise aiming, instant response to gunner input. M46 crews reported the difference immediately. "It's like night and day," one gunner stated. "The M26 fought you when you tried to aim. The M46 goes exactly where you want, exactly how fast you want. It's like the turret reads your mind." This was the Tiger advantage, 7 years late. Implemented not because American doctrine changed, but because combat reality forced the change. Tanker crews couldn't win engagements with traverse systems that fought against precision. The M26 traverse failure wasn't a result of bad engineering. American engineers understood hydraulic systems. They'd analyzed the Tiger's traverse thoroughly. They knew it was superior. The failure was philosophical. American military procurement in World War II prioritized several principles: standardization across platforms, simplified logistics, ease of maintenance by minimally trained personnel, rapid production with existing industrial capacity, good enough performance over optimal performance. These principles made sense for total war. America was producing tens of thousands of tanks, standardizing components across platforms, using the same electric motors in multiple tank types, simplified supply chains. Designing for ease of maintenance meant crews could repair tanks in the field with basic tools. Rapid production meant accepting designs that worked rather than waiting for perfect designs. The German approach was different. German tank production emphasized technical sophistication for combat advantage, specialized systems for specific missions, intensive crew training to exploit equipment capabilities, smaller production numbers with higher per-unit capability, optimal performance even at the cost of complexity. These principles made sense for Germany's strategic situation. Germany couldn't match Allied production numbers. One German tank needed to defeat 3 Allied tanks. That required technical advantages. Hydraulic traverse was expensive and complex, but it gave Tiger crews a combat edge that justified the cost. The philosophical difference was fundamental. American procurement asked, "What's the minimum performance we need?" German procurement asked, "What's the maximum performance we can achieve?" For most equipment, the American approach worked. Thousands of reliable, good-enough tanks overwhelmed hundreds of sophisticated, complex German tanks through sheer numbers. But for heavy tanks specifically designed to fight other tanks, good enough fire control meant American crews died learning that their equipment couldn't match enemy precision. The M26 was designed to counter Tigers, but American engineers gave it inferior fire control because hydraulic traverse didn't fit American production philosophy. They assumed numbers would compensate. They assumed tactical employment would avoid direct Tiger engagements. They assumed doctrine could overcome equipment limitations. All 3 assumptions were wrong in the specific scenarios where M26s actually fought Tigers. Small unit actions, close to rain, sudden encounters at moderate range. Situations where fire control speed determined who lived. American soldiers paid the cost of that philosophical choice. Every modern main battle tank uses hydraulic or electro-hydraulic turret traverse. Not most. Every single one. American, Russian, British, German, Chinese, Israeli, universal adoption. The M1 Abrams, America's current main battle tank, uses an electro-hydraulic system that combines electric motor precision with hydraulic speed control. The gunner commands traverse through a control handle. Push it, the turret rotates. Push harder, the turret rotates faster. The system responds proportionally, smoothly, exactly like the Tiger's purely hydraulic system. The M1's fire control allows hitting moving targets at extended range while the tank itself is moving. This capability, fire on the move, requires traverse systems that can track, compensate, and adjust faster than human reaction time. Only hydraulic or electrohydraulic systems provide this performance. Tank gunnery doctrine worldwide now emphasizes first-shot kills at maximum range, exactly the doctrine that drove Tiger design. And that doctrine requires exactly the fire control capability hydraulic traverse provides. The Tiger's hydraulic traverse is recognized by modern armor engineers as visionary. Henschel implemented in 1942 what wouldn't become universal until the 1970s. The engineering principle, variable speed turret control through proportional hydraulic systems, is now taught in armor officer training as fundamental to tank design. Military historians studying World War II tank combat have compiled statistics that vindicate German fire control philosophy. Tiger I tanks achieved estimated kill ratios of 5.74 to 1 on the Eastern Front and 4.5 to 1 on the Western Front. Not because Tigers were invulnerable, they weren't. Not because German crews were superhumanly skilled, training quality varied. But because Tigers could aim faster and fire accurately under conditions where Allied tanks couldn't. The hydraulic traverse wasn't the only factor. German optics were excellent, German guns were powerful, German armor was thick. But combat analysis consistently shows that the side that shoots first in tank engagements has approximately 80% probability of winning. The hydraulic traverse gave Tigers that critical first-shot advantage. American M26s, deployed too late and in too few numbers to generate meaningful statistics, showed estimated kill ratios around 2 to 1 against German armor. Better than Sherman's, not as good as Tigers. The difference wasn't armor or gun. The M26 matched Tigers in both. The difference was fire control. If the M26 had been equipped with hydraulic traverse, combat modeling suggests it could have matched Tiger gunnery performance. The gun was capable, the armor was adequate. But the traverse system guaranteed it would always be seconds behind in the aiming race. Seconds that meant the difference between killing and being killed. If you've stayed with this deep dive into the invisible engineering that determined armored warfare outcomes, you understand why these details matter. Hit that like button to help us reach viewers who care about the engineering decisions that shaped combat. Subscribe and turn on notifications. We're bringing you more forgotten stories where one invisible detail determined everything. Comment below. What other World War II equipment innovations do you want us to analyze? Where are you watching from? Do you have family who served in armor units? These aren't just history lessons. These are engineering lessons. Lessons about what happens when you copy the form but miss the function. When you optimize for production instead of performance. When you assume good enough is good enough until soldiers die, learning it wasn't. The Tiger's hydraulic traverse was a detail most people never noticed, but to the crews who faced Tigers, it was everything. The difference between aiming and dying while trying to aim. Thanks for watching. And remember, in engineering, as in war, the invisible details determine who survives.